Okay, so this week I have 5 problems. Couple of them, the first two are probably just warm-up problems, and then the last three will be a little bit more challenging. All right, so first question, I was going to assume that you have read the problems. Basically, you have n questions, and you provided n answers, but somehow you shifted all the answers. So the second question, the answer for the second question is on the first line, and then the answer for the third question is second line, and so on. And the left end, the nth line empty, and did not write the answer to the first question anywhere. So the question is, what would be the score be with this shift, right? So basically, you have a bunch of answers. So you have n answers. Let's just call it 0, 1, 2, 3, up to n minus 1. Then you might have A, B, C, D, and so on. So this is, and then the last one doesn't really matter. So these are the submitted answers, but the real answers are like this. Basically everything shifted down. And you ask, well, how many of them are matching, right? So the only time that you match, right? The only time that you match is if the submitted answer, of course, is the real answer, but that also means that you must have two of the same answers in a row. That's the only way you can match, right? Because if this is the correct answer, you shift it up, then to have it match, you must have two same answers in a row. And that is really the only possible way. So basically, all we have to do is figure out how many pairs of consecutive answers are the same. And there can be many ways you can do this. And I guess it's just a matter of coding it. Um, so let me show you my code. As I said, this is just warm up. So I have my score, I read in n, and I basically just go through the whole n answers, read in the characters, and ask if it is the same as the previous one. I did not even bother storing it into an array, but you could, it doesn't really matter. And as long as the previous is the same as what I read, I add 1. So this is a little trick, I suppose. I test if they're the same, which then converts to 0 and 1, 0 being false and 1 being true. And then I can add that in. And of course, I always remember what the previous one is before I move on the next loop. And I initialize the previous to something that I know for sure is not one of the possible answers that you can get. So the first one will never match. And I guess that's it. That's all we have to do. Okay, so first one should be easy. Let's see the second one. Okay, so the year 2025 has this curious property that it's 1 plus 2 up to 9 squared, which is also 1 cubed plus 2 cubed up to 9 cubed. And you're given a single integer n up to 1000. Output the number of k such that this equality holds. Now, because the numbers are so small, all you have to do is just basically try them all. Add up 1 to k, square it, add up the cubes, and see if they're the same. If you want, you can even do this incrementally. So instead of adding from 1 to k every single time, you can add from 1 to k, and then when you can move to this one bigger k, you just have to add one more. You don't have to start the whole sum from scratch again. That sounds pretty easy, but you might have to be a little bit careful. Why do you have to be a little bit careful? You can have up to 1,000 cubed. 1,000 cubed is 1 billion. 1 billion. Okay, 1 billion should cause you to pause a little bit because the standard 32-bit integers, it's 2 billion, 2.147 billion roughly. So if you were to add up a few of these, it's already over the 32-bit integer limit. Okay, so the main thing that you have to be careful about is that this needs to be 64-bit integers. Apart from that, there's not too much challenge to this problem. So I'll just show you. You read it in, you have I have a variable sum, which is the sum of the first k numbers, and sum3, which is the sum of the cubes, and then answers how many of these k works. So I just loop over all possible k. Now, and then I just add k to the sum, add k cubed to the sum. Okay, don't use pow. Okay, just multiply it 3 times because pow in C++ is actually a floating point function, and it could be problematic if you use pow with rounding errors and so on. And then basically at the end, I just ask if the left-hand side square is the same as the cubes, the sum of the cubes, and if so, I add it. So I could have actually forget about using the answer an if statement and use the same trick as I did before, answer plus equals to the result of this check, and then I print it out. Now, why am I using int64t? For the k, actually, I don't need to, but I was just being, conservative because I have to do this k times k times k. I want to make sure that I don't overflow. Of course, it won't because I know that 1k is at most 1,000 and 1,000 cubed is still okay. But I guess I was just, as I was typing this, I just did it um, with extra safety just in case. So this will work even if you have int64, just int. But if you have just int in this, it will not work. So let me just show you. So here's my submission. So let me just change this to normal int and see what happens. Yeah, that is unfortunate. I guess it actually works. Maybe it's because none of the big numbers, actually it's equal. But, well, it shouldn't work. But anyhow, you should be using integer 64-bit integers. Well, that is most unfortunate. I was hoping that this wouldn't work. Okay, anyway. So that's how you do this, but even though it did work, you should really be using integer 64-bit integers here. Otherwise, you might not be able to hold the results correctly, right? Actually, let me just check one thing. So let's make sure that everything is positive. So if there's some kind of overflow, this could be violated. Hmm. Okay, what am I missing? And it's up to 1000. I can add up to 1. It's possible that when I add k cubed, it overflows so much that it even goes all the way to, no, k is at most 1 billion, so it cannot overflow more than once. Is it somehow that they only give small enough numbers? Okay, so they have numbers bigger than 500. Let's do a binary search on the biggest number that they have. Okay, maybe not quite binary search, but let's just do that. Hmm. Okay, let's do something. Go back to 64-bit integers. So this, well, actually I'll use this. So this would guarantee, this is checking whether they overflow. Okay, so it did overflow, but somehow that didn't affect the answers, probably because there are no answers that big that still match up on both left and right side. Anyway, okay. So in any case, you should probably use 64-bit integers. Okay. All right. So anyhow, let's look at some more interesting problems and more educational problems this week. Okay, so here they give you this kind of complicated formula. And basically the idea is that they give you this distance d and some desired amount s to sag in the center, and then they give you this formula. And then the length of a cable is this. You're supposed to figure out what the length of the cable is, but in order to do that, you need to know what this unknown number a is. So d is s, d and s are given. Um, and then you're supposed to output the answer up to basically 4 decimal places. Now, when they say absolute error, of 10 to the minus 4, it means that the error cannot be more than 0.0001. So that basically means that your answer has to be correct within 4 decimal digits. But that doesn't hurt if you can compute it a little bit more accurately. But make sure that you output an answer have at least 4 decimal digits, because otherwise you won't be able to get it right no matter what. All right. There's this hyperbolic sine and cosine, and they tell you this um, definition of these things, but you actually don't need that, because common math functions, where is it? Here we are. Hyperbolic sine and cosine functions are already implemented since C++11. So you don't actually need that, where this was in 2017, but I guess maybe for some language or something, maybe it's not in the language. But anyway, you don't actually need to worry about this definition. You can just use it. All right, so what should we do? Basically, we're looking for value A that will solve this equation, right? And when you try to solve equations like this, quite often what you want to do instead is, instead of writing A plus S equals to A times hyperbolic cosine of D over 2A, let me just make sure that I got this right. Yeah. You can instead transform it into a difference of the two sides like this, and you're solving of f of a equal to 0, right? This is exactly the same thing. And the problem, of course, is how do you solve this thing, especially with this sort of funny situation. Now, when you have a function that you want to find a root, right, where a is f of a is 0, maybe you want to plot the function and see how it behaves. And if you actually plot it, you'll discover that for positive values of D and S, it will look kind of like this. And it will, whether you plot it or you try a few values, you realize that this function is actually increasing. At least it looks like it, but that may not be the real truth. So how do you actually know? Well, if you really want to know, what you have to do is use some calculus to prove that the derivative, at least when a is bigger than 0, it's positive. Okay? Actually, I guess I'm going to write this. And so you have to do some calculus. And it turns out that, yes, it is true. Well, I'll show you maybe a little bit more math later, but if you know that this is true, then what is the way that we're going to tackle this problem? We're going to find some a, value of a, where f of a, so f of high, it's greater than 0 for sure. We're going to find some value low, where f of low, it's less than 0. And knowing that's increasing means that we can just take a step in the middle, right? Take the step in the middle. And if it's still above 0, f of mid is above 0, you can move the high this way. And then later on, if f of mid is less than 0, you can move the low this way. And we're basically doing a classic binary search where every step we make low and high closer and closer together. And when do we stop? we stuff when low and high are so close together that you can't tell them apart within, let's say, four decimal points, let's say, or whatever number of decimal places that you need. And then you can use either low or high because they're so close together, they're essentially the same. You know that the root it's somewhere sandwiched between low and high. So just take the midpoint or whatever. Okay, so we'll write a binary search where it's bigger than something. Then you compute mid is high plus low over 2. And then, all these are doubles, by the way. And then if f of mid is bigger than 0, then high becomes mid, else low becomes mid. Now you might say, well, if f of high is bigger than 0, if f of mid is bigger than 0, then high becomes mid. And you say if f of low is less than 0, then low should become mid. But when I do else, what if f of low is exactly 0? Well, first of all, because these are floating point computations, this is actually extremely unlikely that it is exactly 0. But even if it is true, then it would just make low point to here, and then later on high would just keep shrinking towards here, and it'll be okay anyway. And then at the end, low is what you, doesn't matter whether you say low or high, it's the same because if you squeeze it tight enough, low and high are basically indistinguishable with the right number of digits. So let me show you my submission. And I'm going to show you my incorrect submission first. Okay, so first of all, there's some compiler because I don't remember why. Okay, so let me show you this first. So f of a, s, and d, that's exactly the function that you're given. A plus s minus a times cosine, hyperbolic cosine of theta over 2a. Now, I read in DNS, and the first problem is, how do I know what high should I use to make sure that initially f of high is greater than 0 and initially f of low is less than 0? Well, I don't actually know. So the trick is I start somewhere, right? So I just set them to be 1. But as long as it's not f of low, it's not less than 0, I keep moving it smaller and smaller. So I go to 1/2, 1/4, 1/8, and so on. And because I'm basically halving every time, it will take me some logarithmic number of steps to get there, to get to the right place. And similarly, to make sure that f of high is actually bigger than 0, I guess I'm a little bit loose on what if it's exactly 0. That's very unlikely to happen. But anyway, when it's exactly 0, it doesn't completely matter. So the most important thing is, so in these things, when I say greater than or less than 0, I guess if you have less than or equal or greater than equal, it's also fine. Anyhow, I just double it. And again, in logarithmic number of steps, you will find a place where f of high is actually bigger than 0. So now we have this always. So we just do this, right? If it's less than 0, if f of mid is less than 0, low becomes mid, otherwise high becomes mid. I squeeze everything. Eventually high and low, I chose 8 decimal digits. So high and low are the same up to 8 decimal digits. So that means I solve for A, it's correct up to 8 decimal digits. Then I plug it in here. This is a formula that they give for the, once you know what A is. That's the formula you need to plug in to get the length. And then you print it. I print 10 decimal places. And I got the right answer for the first case. Second case, wrong answer. Okay, before I go on, here's some math. Okay, so I said that if this is the original equation, I can make a substitution b equals to d over 2a, just so I don't have to deal with this. And then once I make that substitution, it looks like this, and I can factor out the d over 2b to make it a little bit simpler. And now I am working with the variable b, but b actually has a different direction. When a is big, b is actually small, and vice versa. So if I want to show that f of a is increasing, I actually want to show that f of b is decreasing. And then I take the derivative, which using product rule and then the fact, and you have to know a little bit about the derivative of cosine, hyperbolic cosine, it turns out with this. And because this part is positive, we only need to figure out the sine of this part. And then I kind of said, you can show that this part is negative with calculus. Yeah, there are different ways you can do that with calculus. One is using Taylor series, and the other one is to actually do more. Make sure, just try a few points. It's bigger, it's negative, and then also make sure that the derivative of this thing is also never increasing, and so on and so forth. Okay, but anyhow, there's some calculus involved, but or you can just plot it and guess. Okay, but anyway, the point is, why am I not getting it right? Okay, so why am I not getting it right? Now, it says that my answer should be correct within an absolute error of 10 to the minus 4, which means that I need my answers to be correct up to 4 decimal digits. Let's just say 5, just in case. And I make sure that it is correct up to 8 digits. So what just happened? The problem was that while I made sure that my answer is correct up to 8 digits, what am I actually solving here? I am solving for A. A might be correct up to 8 digits, but that's not the answer that I need. The answer I need is it's passed into this function as an A, and because there's d over 2a here, when you divide by a number, especially when the number is small, right? If you have 0.001, then dropping a single digit or making a small change can blow this up quite quickly. Okay, so what I mean by that, if I have something like 1 over 0.00001, okay, that's actually a really big number, right? Even if I'm wrong by a little bit, right, that doesn't look like much. From the point of view of this number, it's very close, right? It's correct up to the first 5 decimal digits. You're only wrong on the 6th one, and it's only wrong by a little bit. But when you divide by 1, that can really blow up, right? 1 over x looks like this, right? Okay, I can't draw very nicely, but something like this. So when x is small, you might be here, and just being a little bit off can blow up this part by a lot. So what should we do instead? Right? So it's not good enough to just say, let's solve for A accurately. That doesn't work, because ultimately I want this to be accurate. Okay, what can we do? Well, there are things that we can do which are not very good. Well, we can say, well, why don't we do, I don't know, 15 digits or 20 digits or whatever, make more digits aggregate, then hope that it will work over here, right? But exactly how much you need, that's a little bit unclear, right? So instead, what we're going to do, this is our final answer, which is this function over here. Actually, I guess we don't need s, but we'll put that up here. So you give me a, I give you this, right? This is what we want. So length of high S and D. Yeah, we don't need the S, but I'll just leave it in here. And now instead, I will do my binary search until what I really want from low and high are close enough. And this time, this is going to work because it will make sure, just put -5, it will make sure that what I'm really computing, it's close enough between the two endpoints. I forgot the S and the D. So let me just make sure I put that back in. And now, let's see what happens. Oh, shoot. Oh, wait. Hang on. This, okay, just a minute. So the reason that here, the reason that might not be right is because length of the high may actually be less than this. So I need to take the absolute value. So that, because it may not be that length of the high is actually bigger than length of the low, and that might actually be negative. And there it is. Okay, so in this problem, it's a little bit tricky, right? We are trying to solve using binary search on this unknown parameter A, but we are not trying to answer that our output is not actually A itself, but rather this other expression that involves A. So when we do the binary search, we have to be careful what kind of accuracy we want, right? And we know accuracy of what. So in this case, it's accuracy of this function, the length of A and D. And so you have to be very careful that you don't just say what is the accuracy on A, but rather the accuracy of this function on the two, the high and the low. Okay. So here's a sort of a binary search example. And the next problem is another problem where you have this binary search, but in a different kind of way. So you have this gym, you have these pairs of dumbbells at different weights. Initially, each row has an equal number of dumbbells, but they're all kind of scrambled up. you want to make sure that all the dumbbells of the same weight are somehow next to each other completely. To move a dumbbell, you may either row it to a free neighboring space on the same row with almost no effort, or you may pick it up and lift it to another free spot. There are two rows, so two racks, so you can actually lift it and move it somewhere else to either rack. This takes strength proportional to its weight. For each pair of dumbbells, both have the same unique weight, so the weights of each pair is unique. Okay, so you don't have multiple pairs of the same weight. What is the heaviest weight that you need to be able to lift in order to put identical weights next to each other? Note that you may end up with different number of weights on each row. After rearranging, that's fine. Input consists of one line containing basically up to 1 million pairs, and two lines each containing n integers, which are the weights up to a billion of the mass of that weight along this row. Every weight in the input appears exactly twice. I will put the weight of the heaviest dumbbell that must be moved in order that all items can be paired up while lifting the smallest possible maximum weight. Okay, so what is the problem here? The problem is you have a bunch of numbers. Let me just use this example, 218. Let's see. Oh, by the way, that's the second example. It's simple, I guess. When everything is sort of already paired up, then you don't have to do anything, right? So 0 is possibly an answer because in this case, it's already done. Okay, what about this one? 21828, 21828, and then 99414, 99414. So you can scan both of them, and you realize that they're not all paired up together. So you know you have to move something. Okay, now the weights here from 1 to 9. So the answer, it's always less than or equal to 9, right? Because if you are allowed to lift a weight of 9 or below, that means you can lift everything, rearrange whatever you want, and that's it. Okay? So 9 is always possible. 0 is always not possible. Okay? And the question is, what is the smallest number that is still possible? So if you look at this continuum, you have from 0 to 9. And in fact, if you want, you can go all the way up to a billion because the billion is the largest possible weight. It is always possible to lift every single weight and rearrange things. And if it's not already solved, then it's impossible to do nothing, right? And in this particular case, here's a very important fact. If you have a weight such that lifting so if you have some kind of a max weight, so that if you use that, right, so this is your answer, so that if you lift that weight and anything below that to rearrange stuff, and it's possible to arrange things in pairs, then so is any other weight, max weight above it, right? So if you can solve this problem by lifting only, I don't know, anything 4 and below, let's say, then you can also solve the problem by lifting anything 8 and below, 9 and below, and so on. So in other words, if the answer here is the smallest possible way that works, then everything up here are all possible. And similarly, if you have something that doesn't work, so if you cannot solve the problem by lifting anything 4 and below, then you definitely cannot solve the problem by lifting anything 3 and below, and so on. So if something is impossible, everything is impossible from that point. So if answer is the smallest possible thing that way that works, then everything else below that is impossible. And our goal is to find this smallest possible thing that works. Now, whenever we have this situation where in this range of possible answers, from 0 all the way to the maximum weight that you're given, and you have this exact behavior where on one, it is one answer, or one, whether it's yes or no, doesn't matter. It's one type of answers, and then there's a change, and then it's the other type of answers, and you're trying to identify exactly when it changes, you can use binary search, possibly. And what you do is you basically say, okay, I know 0 is impossible, I know 9 is possible. So let's take a stab in the middle, wherever that might be. If it's impossible, then I know that all of these things below me are impossible. So my answer is somewhere here. If, on the other hand, it's possible, then I know that all of these things are above me. So the answer is somewhere here. And this is what some people call it binary search the answer. Binary search the answer. So the answer that I'm looking for is the maximum weight that I have to move. And then if I know what the answer is, if I know what is the maximum weight I can move, then I want to know if that actually works, possible or not. And then based on that, I can adjust. So the next question is, how do I know, given a certain weight, does it work? So let's say the maximum weight I can remove is 1 in this case. So if I can, the maximum weight I can remove is 1, I can remove these two and put it anywhere. And I can put them in the beginning or the end or whatever, side by side. So effectively, I can just ignore them. Nothing else I can move, right? So what do I do now? Well, I just remove them and then see if the rest of them are adjacent to each other. And in this case, no, 2's are in the wrong places. So that means 1 is still impossible. Okay, so let's go back to here. And let's say later on I want to test, I don't know, 8. So what do? I remove everything that's 8 or less, and the rest are in pairs, so I'm good. So 8 is possible, and so on. So for any particular answer that I'm testing, all I have to do is scan everything that is not, or that is bigger than that answer, because those are the things I cannot move, and make sure that they appear in the right order. And that's it. Because everything else that I can move, I can put them anywhere to make sure that it works. And so this check can be done in linear time. How? Well, I have 2 arrays. I just scan from left to right, ignoring everything that is less than or equal to the things I can move. And then whenever I see something, I just ask, is the thing to the left? Well, first, if it's the first thing in a pair, if it's an odd number of things left, then we just remember what it is. And then if it's an even number, you look before and see whether the last thing that you read was the same. And you can do this in linear time with a scan. And then the binary search, basically it's log 2 of the max weight in your set. In this case, it's 9, but in general, it could be a billion. So basically, the complexity is this much. This is a binary search. And for each thing that you're testing, it takes linear time to check. And of course, log 2 of this is 30. So this is actually quite fast even though n is big. N is a million, so this is at most 30 million. So in this case, what we're saying is, if somebody gives you the answer, can you check if it's possible or not quickly? And in this case, we can't. And at the same time, we have this structure where the numbers, the answers will change from impossible as you go up and then to possible, right? And then once it's possible, it's always possible. So how are we going to do this? We always make sure that impossible is the low and possible is high. And so we can set low to be 0 and high to be, let's say, a billion, right? The maximum possible weight. Or if you don't want a billion, just set it to the maximum weights in your set. So it's not always 1 billion every time. Doesn't really matter too much. But low, it's in fact can be possible if the if every weight is already arranged in the right order. So you just check if 0 is possible at the beginning. If it's possible, that's the answer. Otherwise, you can then say, go into the binary search. And then you'd say, wow, high minus low is greater than 1, right? So what do you want? You want high and low to basically squeeze together so that they touch each other, next to each other, okay? So as long as they're not next to each other, you do what, right? Mid is low plus now. This is the better way of writing binary search for integers. For floating point numbers like the previous problem, it doesn't actually matter. But here, this will make sure that there's no overflow even if I am at the high range of this. Actually, because every number is between 0 and a billion, the best, even if you do low plus high over 2, low plus high can get at most 2 billion, so you're not going to overflow. But this is safer just in case. And then you would say if, so you write a function to check if something is possible, then high is equals to mid, otherwise low is equals to mid. And then at the end, well, when you get out of this binary search, it's always true that possible still goes with the high bound and low always goes with impossible. And when they squeeze to each other, then you know that high is the answer because that's the smallest possible weight that still works. Okay, so let's show you what this is. Okay, so W is, actually I wrote this a while ago, but anyway, so I read in the N, I make sure W and W2, those are the two rex weights, have the right size. I read it in, and then I check. So I'll show you the possible function later. If 0 is possible, then I'm done because it's already solved. Otherwise, low 0 is not possible, so low is 0. High is just the maximum of the two Rexit rates. And then this is basically the binary search as I just wrote on the whiteboard. So how do I check if something is possible? Well, possible, I just check that both Rex are correct. So how do I do that? Basically, at this last, that remembers what is the last thing that I read at the beginning is -1 as I scan left to right. So I scan from left to right. If the weight is less than equal to G, I ignore it because I can just pick them up and move them wherever. Otherwise, things are not, these are the weights that I cannot move. So if it is the second one in the sequence, and if it's not the last one. So in other words, let's say I have something else before me, so I'm now no longer in a correct pair, I return false. So it's not possible. Num++ just keeps track of how many things I have to keep and not move, and I remember what is the last one. And then at the end, I just made sure that I actually have an even number of things in the rec, right? Because I could, the way that I check this, if I have something like, I don't know, 8, 8, 9, it would check that this 8 pairs with the last one, which it's okay. This 9, it would just say, well, there's nothing to pair with, so it's fine. And now I run out. So that's not fine because now I have an odd one out. So this last check just makes sure that I don't have an odd one out. And of course, this is clearly a linear time loop. And that's it. I suppose actually it's not n times 30, it's 2 times n because I have 2 recs of size n, but a factor of 2 doesn't really matter too much. So this is another binary search problem. And it is a very useful tool sometimes. If somebody gives you an answer and you can easily check efficiently, and there's a structure about the answers being, if it's all the small numbers up to a point, it's one type, and then after that point, it's the other type. In this case, it's possible, impossible. Then you can use binary search to help you quickly find the answer that you're looking for. Okay, the last problem is, I don't know if I want to say it's really easy or really hard, but it just, so you have a bunch of rectangles and you want to know what is the total area. Okay, but they're overlapping. And there's up to 5,000 rectangles. Each one have coordinates up to between negative 1,000 and 1,000. Okay, so of course, if they're not overlapping, then it's just really easy, right? You just sum them all up and that's the end of that. But the fact that they can overlap, right, in very strange ways, let's say like this, right, that creates a lot of problems if you try to compute the area. So why am I saying that it's really easy? The reason why it's really easy is because it's a so well-known problem that if you go to the code library, it is not in our normal code library, but if you go to ICPC, and doesn't matter which one, let's say the North American Championship 2020, the last time we advanced to the next stage, you can scroll down and it will say union of rectangles. Then you click on it. Here's a code. You paste it in. There's area, union, rectangles. It's a vector of rectangles. It'll give you the area. What is the rectangle? It's just the corners. So here's my code. I copy this stuff. I read in the answer. I read in the input. I call the function. That's the end of the story. Okay, but if you recognize this and you know that we have code for it, then of course that's great. But part of this summer practice, it's not just to make you familiar with some of these standard problems in code library, but maybe also tell you a little bit about how this works. So let me tell you a bit how this works. Okay, so how do you tell the area of this rectangle? Well, of course you just say, well, let's multiply the height and the width. Okay, but maybe we do something a little bit different. What we're gonna do is we're gonna say, let's scan our rectangles from left to right. Now, of course, we just have one rectangle right now, but let's just say we scan from left to right now. And the only thing that can happen interesting that can happen is when we hit x1 or x2, right? Until you hit one of these, nothing really changes. So we hit x1, and what are we going to do? We're going to remember that there's now something from y1 to y2. Okay? So if we're sweeping, this is sometimes called line sweep algorithm in geometry. We're sweeping from left to right and see what happens. And the only time that anything interesting happens is when we hit one of these x values of a rectangle. So when we sweep and we see x1, we know that now we have to worry about y1 and y2 because now we have this under consideration. As we sweep this way, the next thing that happens is when we get to x2, and we now know that while we still have this y1 and y2, we have swept this much. So now we can say, as we sweep this way, we can look at this way. Now we can say, we can add this area to my consideration. But at the same time, we say, from now on, get rid of y1 and y2. We don't no longer have this little line that we have to worry about. So later on, we sweep and we see another rectangle like this, we will start from scratch. Okay? Now, what else can happen? Maybe you have something like this. Okay, so I'm not going to use explicitly all these x1, x2, and so on anymore. Let's say you have two rectangles like this. Okay, same x's, but different y's, no overlap. As you sweep, you will now have two intervals. Actually, let me just draw it the other way. You now have two intervals that enter this system. So you have to keep track of two intervals. And as you scan through, you will then realize that these intervals will now exit. But before you exit, you sum up this length and this length together, and you multiply by the length of the sweep from the point that you enter to the point you exit. Right? It actually doesn't matter that they are separate rectangles. You just can just add them up, the total length, and then multiply by the distance x you travel before you get rid of these intervals. Okay. Okay, let's do something more complicated. What if you have something like this? You have two rectangles. They start at the same place, ends at the same place, but overlap. Now you have to be a bit careful. You have to keep track of the intervals, right? With overlaps. So somehow when you exit, you need to know that you actually exit both of them, but you have to keep track of the overlap so you know that the length is not just the sum of these two, but whatever that length is. Okay, let's do even more complicated situations. Let's not all start and end at the same x values. Let's say you have something like this. So when you sweep this way, first you will have an interval like this. And then when you get to here, you will now add a new interval which overlaps with the previous one. So now you know that the length of that whole thing is here. But before you do that, you realize that you got to take care of the old interval length plus how far you travel on the x direction and add that area. Then you see that it is now the end of this long rectangles. And so you add up this area, we move this, but you also remove this long interval and somehow you realize that whatever remains is this. So your interval is now what you had before. And then when you exit here, you would remove everything, and then you would sum up the area. So what you need is a way to keep track of intervals, possibly overlapping as you go. And what you need actually is what is called a segment tree. And there's a video in my other data structure series that talks about segment tree. And in fact, we can actually pretend that all these values, the x values are just 0, 1, 2, and 3, and the y values, so this is x, and the y values in this case are just 0, 1, 2, and 3, because those are the only interesting x and y values. So even if this is maybe, I don't know, 5 and 30 and 43 and 75 or whatever, we're just going to pretend that there's 0, 1, 2, and 3. The areas, of course, are going to be wrong. But when we actually sum this up, we will then look up and say, well, this is 0 and 1, but actually it's 25, and so on. And then we can do the calculations correctly. So this technique of taking only all the important coordinates and pretending that it's 0, 1, 2, 3, and then translate it, it's a technique called coordinate compression. Okay, and this is something that's quite useful because it allows you to solve a problem that might exist in a much larger grid into a much smaller grid, right? If you have in this case, each rectangle can introduce at most two distinct x values and two distinct y values. So if you have 5,000 rectangles, you can introduce at most 10,000 x and 10,000 y values. Right? And then sometimes they might collapse. They might not be the same, the different values, right? But in general, each rectangle can introduce at most two x values and two y values. So if you have 5,000 rectangles like this problem does, you have at most 10,000 distinct x and y coordinates. So basically, you use a segment tree to keep track of intervals from 0, 1, 2, 3, and so on, with adding and subtracting, right? So you can say, if there's something in that for that x coordinate, you add 1. Otherwise, you subtract 1 when you leave that interval. And basically, then you can keep track of how many values actually have something in there, and so on. So if you go and read that, watch that video on segment tree, that's basically what happens. And if you were to look at the code, you will see something about segment tree, which is a specialized version of segment tree that has roughly n 2n values. And you have a segment tree for the y's. So where's the segment tree? So segment tree of the y's. And this sorts, let's see here. So you process all the rectangles. If somehow they're not, it's zero area because the distance in x and the distance in y are the same, you just skip them. Then basically here you push all the y values into this list, and then this just makes sure that if somehow they're in the wrong order, you swap them, and then you push back the segment of x's. Oh, okay, so this time this is actually scanning, and this code scans in the other direction. It scans the y values, and then deals with the segments in x instead of what I drew, but it's really the same thing. And these segments basically have these +1 and -1. +1 means that um, when you scan it, basically it enters the system, and then -1 means it doesn't, right? No, okay, hang on. So no, this is scanning with X. So okay, this is scanning in X because when you are the minimum of X1 and X2, that's when you enter the segment. -1 means you are supposed to remove the segment. Okay, where's the segment? Vector seg. Segment is the types. Oh, yeah, segment is just a tuple that keeps track of what's going on. So it just remembers which X value, which rectangle, and where that's entering. So it knows that basically in this X value it's entering, and in this value it's leaving for that rectangle. And we sort. So this part, we sort this. What does this do? It basically means that we line up all the X values from left to right. And then we will, as we go through the V array, we will basically be processing, entering a rectangle and leaving a rectangle. And as we process this, we would sweep from left to right. The area is the amount, which is so the amount is basically what we have seen in the area, the length of the intervals that's kept track by the segment tree times how far we travel. So the compression, it's based on the array index of this V. And then the values of V are the X values, and that basically says how far we travel times the length of the interval maintained by the tree. And then this basically at the next interval, whether we are entering or leaving, right? So um, yeah, so it's +1 or -1 that basically changes what's kept track of by the segment tree. Okay, so it keeps track. Add will basically add the interval and then either plus or -1, which basically increments or decrements everything in that interval. And then this length returns how many things in there in that interval tree are bigger than or equal to 0. Okay, so for example here, if the population it's greater than 0 in that tree node, meaning that there's more than one, but something in that subtree is greater than 0, then the length is just basically the value maintained by that interval, the y values maintained by that node. Okay, so I'm not going to say too much about how this segment tree works because there's another video, but this is a standard union of rectangle that you scan from left to right on the X value while you're keeping track of the intervals as you scan. And there's only sort of something interesting happens when you enter or leaves the rectangle. And on the one hand, it's very easy if you know that we have library code, but still, it's good that we know roughly how that works if we ever have to use this. Okay, so anyway, that's the problem set for this week. And I'll stop now, and then we'll look at another set next week.